Okay, so continuing from these 5 observations for plotting our root locus diagrams, you can see the first things to do are to consider the loci. Where do they start? So we can look at the value of the parameter at low values, and that will give us some sense of where those loci start. And those would typically be at the poles of the open loop transfer function. And we know that in our poles, we generally have the form. Let's get this out here. So in our general open loop transfer function, we have something like G. Sorry, this doesn't. Okay, there we go. G open loop equals 1 over. And we've got our poles here. One's P1. And so on. And generally speaking, we'll define us as having n poles. So S minus Pn. So we would typically find that our asymptotes start at the poles. And then according to the next piece here, that we tend to the zeros of the open loop transfer function. And if sometimes those are difficult to find, just look at the equation again, let it go off to infinity, and see where that function is tending to go, as we've done before. Then the number of loci is the same as the number of poles. And that's something that maybe we want to test rather than just believe. So what we can do is make use of our simulator. So remember this notebook with tutorial 04, we can use this as a simulator and we can try out a couple of experiments here. So for instance, let's uncomment this and let's use this one. So here we are expecting to see 2 root loci. Oh, by the way, I've got a big luxurious 50-inch screen here, so I need to make this bigger. Okay, so looking at this, looking at this transfer function, if we just run this, we are expecting to see, because we can see 2 poles here, we expect to see 2 asymptotes. So having run this, we can see, yes, there are these 2 asymptotes here. We can see the roots here. So we can see 2 roots developing. And we know to ignore that 45-degree line for now. Right, so this one does meet with our expectation there. And let's just edit that a little bit. Let's see what happens if we add another one. So if we go times S plus 3 and rerun that. Just waiting for that to complete. And so if we look at that one, we expect to see 3 roots now, and you can see here there are 3 roots shown, so 3 loci, and that's 1, 2, 3. And the other thing, well, maybe we should also check what if there are zeros there, explicit zeros. So let's say we have another, let's say we have a term up here. So let's say that's S plus 1.5. Let's see what that gives us. Okay, that one's ready. And we can see here that we still have 3 roots. Adding a 0 didn't change the number of roots. So the number of roots does depend entirely on the number of poles. So it's nothing like poles minus zeros. It is just number of poles that will give us the number of the number of loci equals the number of poles. Okay, then the next part is to look at the next principle there is to find the center of gravity. So the center of gravity is given by this. So we just add up all the poles and subtract off all the zeros and divide by the number of poles minus the number of zeros. and that will give us a number in S, which will tell us where all those asymptotes originate from. And so if we were to sketch it out, I don't have paint on this PC. So there's an online kind of a paint. So if this is our line, then if we find our center of gravity is, let's say, a -3. So let's say it's here. Then we know that all the poles that those asymptotes will be pointing towards that. So for instance, even if there's a root that's doing something like this, that's a bit too wavy. So even if we have something that looks like that, then you can see that this pole, if I have drawn it correctly, is basically pointing, the asymptote here is pointing us back down towards the center of gravity. So the values as they go off to infinity are all pointing at that center of gravity. So you can use those basic principles to sketch out the root locus diagrams for any of those problems that were outlined there. So can I just check, are there any questions or comments on that? It is something that you just need some practice doing. So be sure to work through all those examples given in that in the tutorial. Okay. Any questions or comments on root locus diagrams? Okay, I'm not seeing anything. So the next thing we want to do is, well, we can say now that, yes, we can find the roots of our equation. So we have some open loop equation. Sorry. Right, so we have some open loop equation, and it may have zeros as well. So we'll have S minus Z1 and any number of those down to M, so S minus Zm. Right, so this is the typical, the standard form that we can arrange our transfer functions into. So that's our open loop process. And we know that the poles of the closed loop process are the zeros of the denominator, or so the closed loop process looks like this. So G closed loop equals G open loop over 1 plus G open loop. And so, so the zeros of 1 plus G open loop are the poles of G closed loop, right? So we want the zeros of this. And, and what we want to do now is generalize this, right? So currently, we have to know this function. So this is the limitation to us, that we need to derive an equation to actually control this process, that it's actually not possible to do any of this analysis without developing this equation. And that means we need an equation that fully describes our process. And you see, that's quite hard to believe we'll always be able to do, right? Most of the time in our chemical engineering processes, or in any engineering process, what we actually have is something like a black box. So most of the time we have some unknown process. So if I can try and sketch on this. So most of the time we have some process here, and we don't know everything that goes on in there. And we typically try to do some experiments there. And so what we would like to do is say, well, there's some input to this process, whether that's an inlet flow rate or it's just some other variable around that process that we can influence. And so we want to put some signal in here, and we want to measure some output out here. And we want to try to interpret the response that we get, right? So we'll get some output here in response to our input there. And we are hoping that we can interpret that to give us this function g. And remember, again, g we got from deriving the process. So maybe go back and have a look at that 2 tanks case. So in the 2 tanks case, we developed the material balances, and then we could fully describe the rate of change of the height in each tank. And we reference that to the control variable, the input or the output, one of those. So we derived g. And what we are saying now is there not a way for us to directly measure g? And towards this, we have available to us the so-called basic theorem. And if you check in the Dropbox folder, you now have this additional set of notes there. So that's it's simply titled Frequency Domain Dynamics. So in fact, that's the name of our whole section, right? So now we are looking at actual core frequency domain dynamics. And it's given this name because it involves using a sine wave as the input. So when I said just now, we would like to make some change at the input and measure some output, and I drew a little sine wave there, that wasn't by accident. That's because I know that we are going to use sine waves. And so the frequency response, right? The frequency, it's the frequency of the sine wave that we apply here. And so what we are going to do is apply a series of sine waves. So if you can imagine doing this kind of experiment where we first apply sine waves here of a certain frequency. Yeah, it's quite tricky to draw with this mouse. Bear with me. So that's one. So if you can imagine, we apply a sine wave for a fairly long period of time, and then we collect the response here. And if you recall, when we did the first order case and the second order case, we did find that we got sine waves as responses. So we do expect that we'll get a sine wave out as well here. And then we do another experiment. So we've done one experiment where we've applied a particular frequency. Then let's say we apply a different frequency. So now let's say we use a much sharper frequency. So if the period of the sine wave was, and yeah, sorry, I'm not drawing a sine wave very well here, but what I'm trying to show here is that this has a higher frequency, that the distance between the peaks here, for instance, is much smaller than the distance between these peaks. So we are applying a different frequency in this case, and we expect then to get a different frequency in our response here as well. So the frequency in this case will be higher, and also the amplitude might change. And the amplitude, so even if we haven't changed the amplitude at the input, so maybe this height here was 1, and I haven't drawn it that way, but even if we apply the same amplitude of 1 here at the input, the output might not have the same amplitude. And that's purely because the system has a certain delay in it. It takes some time for the system to respond. And so at a certain frequency, you might get a kind of reinforcement effect that the process rises, or it responds to a change in the input at a certain rate. And when you use a low frequency, you're giving it more time to respond. When there's a lower frequency, or sorry, when there's a higher frequency or a lower period, then there's less time for it to respond. So it might not, in the higher frequency case, go to as great an amplitude. So the amplitudes may change here. Yeah, it's quite hard to draw this. So the amplitude here might not be the same as the amplitude there, even though you've applied the same amplitude at the input. So that's one thing that can happen. What you also might have is that there's a phase shift between these two. Do we have color? Nope. So let's draw this separately. So let's say we apply our, at the input point, Didn't seem to work. Okay, so let's say we apply at the input point this sine wave. And when we measure the response to that, let's say we get something that looks like this. So it might take some time to take off here, and then it will settle into it. And let's say it starts to do this. So our system responds in this way. Then you can see that in addition to there being a difference in the heights here, there's also what we call a phase shift. So the point where the peak occurs here is different to the point where the peak occurs there. So you've got a certain, if you like, delay, or we call it a phase shift. So in terms of the time, there's a certain time difference between those two sine waves. So those are not the same sine wave. We can say, maybe let's state it more symbolically. So if we have, so if we have our u function, so let's say the input looks like this. So u of t equals, and the amplitude there, let's call it u naught, or rather u bar, times sine of omega t. So that's what we are applying at the input. We have a certain amplitude u over bar, and we have a frequency omega. And this that we apply at the input side, and then at the exit, we will get a certain response, which we'll call y. And y will have its own amplitude, and it will have the same frequency, but there may be a shift. So we can say here plus phi. So we might find a constant offset between the peaks in u and the peaks in y. So we'll just call that a phi. So phi is that offset difference in time for the two peaks to lie across each other. So we can define two parameters now. We can define the magnitude ratio. So we'll call the magnitude ratio the amplitude ratio. So the magnitude ratio or amplitude ratio looks like this. Oops. So that's your magnitude ratio, and your phase angle. How do we call it in the notes? Let's just have a look. Okay, we don't call it anything, but so I'm just going to write it as. Sure, it's quite a challenge working with this thing. So I'll just call it a phase angle here. So that is our phi. Well, I saw in the notes we were using a theta. So let's be consistent. Let's use a theta here. Okay, so we can see that the magnitude ratio, remember we said that as we apply different frequencies at the input side, we will get different magnitudes at the exit. And so we can deduce from that our magnitude ratio is a function of frequency. So this is a function of frequency. And by the same token, we will also find, if we were to do this, that this delay, right? If you take the peak in each case, you'll find that as you change the frequency, that distance will change as well. So that's a second thing that varies with the frequency. So we can say that is also a function of omega. Okay, so that's, and at this stage, we don't know why we are doing this. I mean, it's fun to just define things like this. We can always propose this experiment. We did play around with inputs of sine waves, and we did see that we would get sine waves out, and they might be shifted a bit, and the amplitudes would be different. So we can always do this, but the real relevance of this shows up here. So if you look at the so-called basic theorem, the basic theorem says that this magnitude ratio is actually the same as our g function, or the magnitude of our g function, if we use s equals I omega. And similarly, this phase angle, this which is simply the delay time, that's equal to the argument. And if you look at this left-hand side, this is nothing but the polar coordinates of g. Remember, g is generally a complex number, and so we can express any complex number in terms of the real part plus I times the imaginary part, or we can express it in polar coordinates using a magnitude and the argument or the angle here. So this is telling us now that this very practical thing on the right-hand side, right? Remember, we just put in some sine waves and we measure out the sine waves, and we can calculate the magnitude ratio and the phase angle. So the right-hand side here is quite measurable. And even if we know nothing about the process, if the process is just a black box to us, we can still go ahead and apply a sine wave at the input and measure an output sine wave. And so we can get these numbers for any process. And now it's saying to us that those numbers are related to the unknown g function. So even though we know nothing about that process, and so we can't write any governing equations, we can't derive g, there's no way for us to get at g because we know nothing. But still, we can do this experiment and we can get this g. And this is quite a specific form of g, right? This is not giving us the whole g of s plane. It's giving us g for very specific values of s, for s being equal to I omega. But still, it's giving us something about g. It's giving us some information about g. And we'll show why this specific line, s equals I omega, why this matters so much. Yeah, any questions or comments there? Right, and I think this is quite amazing, really. And I think in most textbooks, they just say, okay, this is the basic theorem and this is the relationship. But if you really think about it, this is very practical. This is an experiment. And this is the g function that we had no way of getting to if it was a black box. And now suddenly we have a way to actually measure g, a specific part of g, right? G along s equals I omega. But still, it's something that looks like it might be useful. So we first need to just prove this, right? So again, any questions or comments there? Right, so don't just brush over this as if it's just another mechanic to work through. That's the physical meaning here. We are now relating the measurable world to the mysterious world, to the world of processes that we can't, that we don't know anything about. Okay, so as we said here, we can break g. So so let's forget this result for now. Let's just think about g of I omega. So for whatever reason, we've chosen s equals I omega. So s is a pure imaginary number, and it's changing with omega. So omega can go from 0 to infinity. So basically our s values, let's just sketch this a bit. So our s values, if we were to plot s here, so let's say this is the s plane. Geez, this is terrible. So we've got s here, and we could have chosen any line in s. You can choose a line here or a line here. So we are saying, well, we're not doing that. What we will do is pick specifically s equals I omega. which is going to be this line right here, right? Let's use this. So S equals I omega, we are looking specifically at this line on the S plane. And then if you can imagine on the G plane, right? Remember, G is a complex number, generally speaking. So on the G plane, G is going to do something else. So G is going to take on its own complex numbers. And if we try to draw that, well, we don't know. It depends on the process, but G is going to do something. So for these different values of S, we are just looking at the values of S along this line, then G is going to do something as that happens. And then the whole usual, the analysis applies. Does G have roots, positive real roots? So here I've drawn a positive real root. Then we can say, oh, this is going to be unstable. But anyway, that applies specifically for S equals I omega. So just be clear about that in your S plane, we can pick different values of S. We are free to pick values from the whole plane, but for some reason, for now, we are just picking S equals I omega. So we are looking at S values along that line, and then G responds in a certain way after that. So that's what we're looking at currently. And let's go further with that. So we've expressed G in the kind of rectangular coordinates, and we can also express it in the polar coordinates. And we can also we can also relate the two. We can say that the magnitude here is, of course, the square root of the square of the real part plus the square of the imaginary part. And we can also say this phase angle, so arg of I omega, that's equal to the arctan of the imaginary part over the real part. So that's all just standard complex number relationships, right? There's nothing different there. So now let's look at why is I omega so interesting to us. So we want to prove that this is true, that this basic theorem applies, that this experimental world can be related to the unknown G world in this way. So let's just start with a general, let's start with a general process. So whatever this unknown G is, it's sitting over there. And we have the output variable y. So in the Laplace domain, we've got a y, a capital Y, and then we have an input u, so a capital U. So that's the standard transfer function definition. Now, if we are applying in the real world, if we are applying a sine wave input, then if you look in your table of transfer functions, and I think we also derived it as well. So look back at the first or second lecture where we derived the relationship, where we did the Laplace transformation of sine. You'll find that we got this expression, right? So if you take our input u over bar sine of omega t and you Laplace transform it, then you'll get u over bar as the constant amplitude times omega over s squared plus omega squared. So that's your Laplace version of your input function. And looking at this denominator, we've got s squared plus omega squared, and we know we can factorize that as s plus I omega times s minus I omega. And just check, if we multiply this out, then we'll get s squared. So there's our s squared. Then you multiply s minus I omega, and then you've got s times plus I omega. So those two will cancel each other out. And then you have minus I squared omega squared, and I squared is -1. So the minuses cancel, leaving us with omega squared. So just check you agree that this multiplication here gives us s squared plus omega squared. Okay, so that's just at the input side. Just any questions or comments so far? Right, so that's at the input side. And then we have our general transfer function. So although we are not sure that we actually know what that transfer function is, let's just propose that there's a general form like this. So in our transfer function, we'll have a certain number of zeros, we'll have a certain number of poles, and we may have some constants and yeah, A and B like that. So generally speaking, we can say there should exist a form. So whatever the function g actually is, we could use Taylor series expansions and stuff like that to get it to a form that looks like this. Okay. And then if we stick it all together, right, if we come back here, we've got y equals gu. So we've got a general form for g. So we'll keep that form here for g, moving the a and b out in front here. And then for u, we've got this u over bar omega over that, right? So that's the equation if we write it in terms of y. And then we also know that we can use partial fraction expansion. So remember, again, in the first or second lecture, we talked about if we have our denominator factors like this, we could rewrite that as the sum of terms with the denominator, which is each factor. So we can take an s plus I omega, and there's an unknown a here. And this a is not generally related to any of the constants here, but there's some constant value a. And then similarly, there's some constant value b, and we can take that factor and so on. So we can propose here that whatever this function looks like, we expect we can factorize it and get a form like this. And then the question is just what are these constants a, b, c up to z here? And so to get those, we said typically what we would do. So for instance, if we wanted the value for a, we can see if we multiply the left and right hand sides by s plus I omega, right? If we multiply y times s plus I omega, and we multiply everything else here by s plus I omega, then we can see if we apply, then we'll have a plus b times s plus I omega over s minus I omega plus c times s plus I omega over s minus p1 and so on. Then if we choose s equals minus I omega, right? If we just take the value that makes the denominator here 0, then when we multiply that out, all these terms will vanish. So these will just go to 0 because s plus I omega becomes 0 at s equals minus I omega. So all those terms vanish, leaving us with that a equals the left-hand side. And if you look at that, we can say basically that that is the same as, if you look back here, that is the same as omega times u over bar times, so all this stuff, sorry, one second. So we've gotten rid of all this. S minus I omega. So here, so here, if you look at that y, so looking at this y here, and if we multiply this y by this denominator, s plus I omega times s minus I omega, if you multiply that out onto the side, then, and then you multiply here by s plus I omega, then those, the other terms cancel, leaving us with just simply this term. Right, so you can say this is the same as this form here, or in other words, your left-hand side here is the same. This y, remember, is the same as u over bar time, u over bar times g. So let's just write it out here. Sure why this word, it always takes a long time. So we can say here that y equals it's u over bar times u over bar times this stuff. So omega over s plus I omega. Let's see. So that's our u part, and then times g here. So if we look back at what we have right here, that's all it is, right? We've multiplied by s plus I omega, so that part is cancelled out, leaving us with this. And we are looking for the limit as this goes to minus I omega. And if you apply that, when you use s equals minus I omega, when we have s equals minus I omega, then you can see in this denominator here, we are getting minus 2I omega. So that's what we have down here. And then you've got a minus 2I omega in the denominator that can cancel with this omega in the numerator, leaving us with just u over bar over 2I, g of I omega. So our constant A looks like that, right? So that's how we can get our A. And if you follow very similar steps for B, then you'll get that for B. Okay, so that's how we get those two constants. And then we know the similar thing applies for all the other constants that come from the G function. So if we simply take the multiplying by that denominator on the left-hand side, and then we take the limit s goes to the pole, then that's going to knock off all these other terms, and that will give us the constant that we are looking for there. So those give us all those constants. And then what we can do is take this back into the time domain. So we have a nice form now, right? Once we do all that, we have a nice form that we can use. We can say, well, we've got the time constants now. So there's a time constant of I omega here, another one of minus I omega here, and then P1, P2, P3 up to Pn there. So we can say that we can go back to the time domain. Remember, 1 over s. It's always such a mission here. Remember that if we have a Laplace transfer function, so the inverse Laplace, so inverse Laplace of 1 over s minus a, that's equal to, so the inverse of all this, maybe we can make a kind of new operator here. So we can say raised to the minus L for inverse Laplace. That's equal to e to the at, right? So all those are our time constants. So if we look at, when we go back to the time domain, those time constants will show up in here, right? So there are the time constants, and we've just figured out what the constant in front is. So those ABCs and so on, those show up here, right? So we can now fully specify what our solution looks like. And all this is still general. It's we don't actually know the value of P and so on, but it's starting to look like we can extract it from that experiment. How are we on time? Okay, 3 more minutes. So here, if our process is inherently stable, right? So this is an assumption. Let's say we are trying to control an inherently stable process. We just want to get onto set points faster. Then all our P values will be negative. So we know that as time goes to infinity, all these terms will vanish. And so our response is eventually going to look like this. And if you look at this equation, you can see that we can represent this differently. So first off, we can look at each of these functions. So g of I omega, if we just expand that, right? So I'm not, sorry, here. So I'm not trying to do a multiplication here. I'm just saying here, g of I omega, we know we can rewrite it in polar coordinates like this. And then here we've got g of minus I omega. So we know the magnitude is this and the angle is this, right? And the complex conjugates being equal means that the angle minus I omega, it's the same as minus I of the same angle. So we can apply that expansion. And if you substitute for g of I omega and g of minus I omega in here, then you can see you have these exponentials and you are multiplying by e to the I omega t. So you can group these in with respect to I to look like this. So each of these terms, after substituting this, you can group them in like this. And then looking at this, you've got your magnitude. So if you just divide through by u over bar for the y here, and you keep the magnitude here, then you can recognize this as our sine wave, right? So have a look at your Euler's formula. And we did talk about this before. We showed that if you add, if you take the left-hand side of Euler's formula and you apply the negative of the angle, then the cos parts cancel and you'll be left with the sine part. And so the two can cancel, and so we are left with this. So just check back in the notes, and we did show from the Euler's formula that you can do this. So we've now shown that that is the time response. And what's nice is now that we have this time response version, we can identify here that this is our magnitude ratio. And we can see from this that the left-hand side is the magnitude ratio. On the right-hand side, the sine wave here, the maximum value is 1. And so our amplitude, the value must be this magnitude of g of I omega. So we've proven that the magnitude of g of I omega is equal to this amplitude ratio or magnitude ratio here. And then you can see that this is the angle or the phase shift. So the phase shift theta is the same as the argument of g. And so this proves what we were looking for, that we can do a simple experiment. We can measure the magnitude ratio and the angle, and we can use that then to infer the value of g at specific s values. Okay, so that's what we wanted to prove for today. Are there any questions or comments there? So please be able to work through all this. It's not a long proof, and it's just that you might need to brush up on your Euler's formula. Just work through all these steps. This is all very simple algebra, and you can prove the basic theorem. And it really says something quite amazing. It's a pity that it's not kind of stated more dramatically in the books and so on, but this is really a fantastic result that will enable us to control even a process that we know nothing about. Okay, at the moment, we can't completely see the relevance because we are stuck to this very specific S line, but we'll get there. Okay, any questions or comments? Okay, if not, that's it for today. See you next time.